Coming up next, we have Vincent Benzoni, aka Guillotine, with Quantum Conundrums Conquering that's hard, Quomputing Challenges. Thank you. Good luck.
Hello. Yeah, perfect. Hello, everyone. Nice to meet you. Is it better? Yeah. Nice to meet you. So we're here to talk about quantum computing and its fun stuff. I'm going to tease you. If you stay long enough at some point, at the beginning will be a bit like a lot of physics, some physics, not everything. But if you stay long enough, you will see actually quantum algorithm. So we're going to break RSA on a quantum computer in the cloud live, I hope. By the demo gods, let's pray together. If you believe in something, you can start praying now, but it should work. So let's start the fun stuff. And it's not working. Okay, perfect. So who am I? I'm Vincent Benzoni, Guillotine. You can probably tell this by my accent. I'm French. You can ask me to repeat stuff if you want because my accent is not perfect. I don't mind. I will not be offended because I know how to correctly pronounce croissant. And other than that, why I'm here in front of you today, I used to be a researcher in condensed matter physics. I hold a PhD in this field. And now I'm a cybersecurity engineer for the past few years. You can tell that I'm kind of like a Schrödinger cat between physics and cybersecurity. And you have a picture of me right there when I was young and fresh at the beginning of my PhD. So today we're gonna start to understand and see why quantum computers are a threat for cybersecurity, and what is the actually problem around them. We're gonna start to understand what are quantum computers. Then we're gonna see actually what quantum algorithms are a real threat for us. And then we're going to see actually when you run quantum algorithm, you run them on hardware. So we're going to see quantum computers, the real quantum computers are running the quantum algorithm. Then we're going to see if everything is in place like this, what's the threat timeline, the risk, and what are the solutions that already exist. And then we'll have questions just to see if you're not dead or if you're dead or alive. So, introduction. The quantum apocalypse is coming, be very afraid. So this is something you heard a lot in the news. This is some marketing shit. The idea behind this is a sufficiently powerful quantum computer can crack in relatively short time an RSA key, an ECDSA signature, or Diffie-Hellman exchange. So here I want to emphasize sufficiently powerful, relatively short time, and quantum computers are doing nothing more than this. It's no more like a threat than this, but it's already a lot, okay? It's already a lot, but it's not like actually everything you will do in your life will be done, will be gone if quantum computers arrive. So here we're gonna understand the whole point of this discussion and this presentation is to understand actually what are the real threats, and when we identify them, actually we have already stuff in place that are being put in place to minimize the impact of quantum computers on our job, cybersecurity, and on our digital life. So let's start with what is a quantum computer and what is quantum computing. So quantum system is a system that displays behaviors which can only be described by quantum physics laws. Quantum physics laws are a particular set of laws that were described and discovered at the beginning of the 20th century by guys like Einstein, Heisenberg, and all those fun guys. So just to make stuff pretty clear, those two things here, quantum healing and how you can heal your body with quantum, and here it's a vibrator, which is quantum in any way. Those stuff are not quantum. They are marketized as quantum, but actually there is nothing quantum either with your body or either with your vibrator. Quantum computing is the idea to build a quantum system designed to leverage its quantum properties to compute some algorithm, okay? So we're gonna start to understand and do a parallel between classical computer and quantum computers. So you have the hardware at the base layer, right? Then you have the data that is living on the hardware. Here it's bits, and you will see on the right side for quantum computers, we call them qubits. Then you can do operation on this data. So this is the typical gates you will see. So on the left side, you have what we call logic gates, and on the right side, you have quantum logic gates. We'll go in the details bits and operation later. And when you have those two things, then you can have like data that you can play with, either numbers, either like letters, whatever. It's a representation of the world around you that you decide. So the first thing here to understand is not the hardware, because like it's actually not easy, but more like graphic. The real like magic is around the bits. So here we're gonna compare a bit with a qubit. So a classical computer works with bits. Bits are either 0 or 1, right? A quantum computer works with what we call a qubit. A qubit is actually a lot of stuff. A qubit can be 0 and 1 simultaneously, and usually the way we represent them is with this. It's not the sphere actually, it's more the hour pointing in the sphere. So here you can see that the hour is pointing up towards the 0, which is a qubit equals 0. Or it could be pointing down, which is a qubit equal to 1. Or it could be somewhere on the sphere. So like if you think of this is 0, this is 1, then it could like basically do whatever it wants, like if it rotates like around the sphere, right? So here it will be in like two superposition of state 0 and state 1. Here will be 0, 7 for state 0 plus 0, 7 of state 1. Here will be 0. Those are not real numbers related to the arrow, but like it's the idea. You have like what we call whatever superposition of state 0 and state 1. And this is actually the first thing that is crazy about quantum computing, is that actually you are not either one or the other. You can be one or the other, but you can also be actually a superposition. So you can be two times, you can be both at the same times. This is like, if you've heard about the Schrödinger cat, this is what it's behind the Schrödinger cat of being dead and alive. It's like two states that you think are opposite, but actually the system embodies those two systems at the same, those two results at the same time. And now that we have one qubit, we're gonna add another body to the party, right? So for we have two bits in this case, so bit 1 and bit 2. For a classical computer, to describe those states, you have 4 possibilities, either 0, 0, 0, 1, 1, 0, or 1, 1. For a classical computer, so if you take 2 qubits, you bring them together closer enough, they will become what we call entangled. Entangled means that like actually you're gonna see the system as not two different like subsystems, but you have to think the system as a whole. You cannot like absolutely cannot modify only the right part of the system without impacting the left part of the system. Everything starts to be united. And this entanglement is give us the possibility to write quantum states that you can see at the bottom, which are 0, 0, 0, 1, 1, 0, 1, 1. And then you also have the superposition of states, which is they can be in any superposition of all those states, right? So here, because of entanglement, we have those two numbers, 0, 0, or whatever, or 0, 1, plus the superposition, which is the plus sign between those states, right? And now we have those two, like, we have the two main components to build quantum computers and the two like main quantum properties that we're going to leverage in quantum algorithm. So quantum computers are made of qubits, and those qubits have can be in a superposition or can be entangled together. And a quantum algorithm will be the manipulation of those qubits using foreshadowing quantum logic gates. And this will give us the possibility to solve problems. And those problems can sometimes be exponentially faster than like the way we solve those problems, sorry, it can be exponentially faster than like the way we are solving those problems with a classical computer. And this is where it gets crazy. So this is what we're gonna see in the second part, which are the quantum algorithm that threatens cryptography. You have to understand that like quantum computers can run a variety, well, difficult word to say, the variety of like algorithm, and you only have basically 2 algorithms that are really a threat for cybersecurity. And when I say cybersecurity, I say like our encryption, the way we do encryption at the moment. The first one is the little brother. I'm going to show you the big brother at the end. is what we call the Grover algorithm. So Grover algorithm was discovered by a guy named Grover in 1996. So you can see it's like not too long ago, but also it's been a long time, and we know about those algorithms for a long time. And this algorithm basically is like a way to do brute force and to find it's how you do search in a list of unordered items. So basically, it's like how you improve brute forcing. The speed up of this algorithm compared to classical algorithm is the square root speed up. What it means is like if you had 1 million operation on a classical computer, if you are able to do this on a quantum computer, it will only take you 1,000 operation. So if you had to do something in 50 seconds, it takes you 7 seconds. You're like, okay, it's kind of like a big speed up, but it's not like that crazy. Actually, if you do this and if you come to see your manager and say, oh, I've done this kind of speed up, I hope you get a raise or a bonus or something. But it's not like super threatening, right? Now comes the big boy. It's the Shor algorithm. The Shor algorithm is why you heard about like quantum apocalypse and everything. And there's only one algorithm. Like you have many algorithms that exist that have no impact on the encryption that you are using at the moment. The only algorithm that exists at the moment that is a real threat is this one. This one was discovered in '94 by a cool guy named Shor, right? And this one has the beautiful idea to basically break RSA, ECDSA, Diffie-Hellman, and everything. The problem with this guy is like you will be able to decrypt those like those encryption algorithm, so RSA, let's say. And the operation to do the decryption will be exponentially faster. So usually exponential is something pretty difficult to grasp for a human. So what it means is like if I want to decrypt an RSA key with like a classical computer, it will take me 10 to the power of 26 years to do this. It's longer than the age of the universe, right? If I do this with a like pretty powerful computer, quantum computer, it will take me 1 day. And this start to be a real shit show, if it exists. So now you have those two bad boys that are here, and basically Grover algorithm is like, okay, yeah, sure, we can do stuff that like are pretty easy to implement at the moment, without like disturbing too much the way we do stuff in our, let's say, tech stack. But Shor algorithm is on the other side a real threat if it's one day like will start to be really useful and be cryptographically impactful. And this is what we're going to see. So we're going to focus on the Shor algorithm first, and I'm going to explain to you why it's a problem and how it's a problem. And for this, since it's RSA killer and this is the main protocol we're using, we're going to explain like RSA and like what's the idea of like asymmetric cryptography. So RSA is working because if you take a prime number and you multiply it by another prime number, you have a big number. Those prime numbers, prime 1 and prime 2, becomes what we call a private key. And the big number you have from the multiplication of prime 1 and prime 2 is what you call the public key. Now enters Alice and Bob. Alice has his own private key and his own public key. If Bob wants to send an email to Alice, right? Bob can send an email to Alice, and if he doesn't use any encryption, this email will be unencrypted. This email being unencrypted means that like if I'm listening, if I'm taping the network, I can see actually what's inside the email. This is usually not something you want. So what they come is like using this big number, so the public key of Alice, Bob can actually do a mathematical operation to encrypt the message and to get an encrypted message, and then can send this message to Alice. And Alice is the only one, foreshadowing, yeah. Alice is the only one that can decrypt this message with her private key, right? Now enter Eve. Eve is a bad girl, and she wants to decrypt this encrypted message. So Eve, at the moment, what happened is like actually Eve can like take the encrypted message by tapping the network, and actually it's safe because to get this big number from like, do you remember this big number in red, in violet, was actually coming from the multiplication of two prime numbers. If I only have the big number, and I'm trying to do the operation, but on the other way, so I have this big number, and I try to find what are the two common prime factors, so this is the real term behind this. Doing this with a classical computer is actually, it takes a long time. We don't have a good algorithm to do this. This is what takes the age of the universe to do this on a classical computer. Now, if you have a short algorithm, and if you have a powerful enough computer, taking this big number and getting the two prime numbers will take you 1 day. And this starts to be a problem, because then it means that I can get your encrypted message, take this message, put this in my quantum computer with the short algorithm, and then I can have your private key, and then basically I can decrypt your message. So this is the real threat behind this, and this is why it's the RSA killer. And once this is happening, you will have kind of a domino effect. So if this exists, you kill everything that is related to RSA, ECDSA, so elliptic curve crypto, and Diffie-Hellman exchange. And this means basically that all those protocols that we're living with, HTTPS, SSH, VPNs, code authorities, code signing, all of this, and Bitcoin transaction and Ethereum transaction are in a way or another relying on those specific cryptographic algorithm. And those algorithms will basically be useless if you have a quantum computer with the short algorithm, a powerful enough quantum computer with a short algorithm running on it. So this is the real threat, and this is the problem. So now you want to understand, so if we go back to the stack, I've been talking about quantum algorithm, and you're okay, sure, you're nice, Vincent, but actually what's a quantum algorithm and what does it look like? So if we go back to classical and quantum computer, the comparison, on a classical computer, at the base, the way when you do any type of coding, at the end, you'll end on the hardware and you will use logical gates. So you have different type of logical gates, and with those logical gates, you assemble them and you have circuits, and that's how you do programs. You will do the same with quantum computers, but you will use quantum logic gates. Here you have a CNOT gate. Here you have what we call a Hadamard gate. You can see that some are similar to what you will find in classical world, and some are really specific to the quantum world. In this case, the Hadamard one with the big H is definitely something that is only that only works on qubits. So it only exists and only works in quantum computers. With those gates, you will do the same thing. You will assemble them, and the way you will assemble them will define your circuits and your algorithm. You can see here you have 4 lines, 4 horizontal lines, and I have each line representing a qubit, and basically my qubits will go through different gates. Those gates will represent different operation that I will apply on the qubits. And so let's say the first one will have an Hadamard gate, then the second one will be used after the Hadamard gate to do what we call a CNOT, and basically you will go through the whole circuit, and at the end you see those little sign like this. You will measure those qubits, and the representation of those qubits after you measure them, after they've been through those operations, will give you the result of your algorithm. And that's the idea behind a quantum algorithm. The thing you have to understand is it looks it's pretty similar in the way we're doing a classical algorithm. The only thing is we're touching the quantum properties of our objects. So in this case, I told you, you have the Hadamard gate, which is the big H, right? The big H will touch is only working because you can do superposition. It's you see, you have here, I told you at the beginning, you have a qubit with 0 here, qubit 0 here. If it goes through the Hadamard gate, I will have a superposition of its state being 0 and its state being 1 with certain coefficient right there, right? So now that we understand what is a quantum program, what is a quantum algorithm and quantum, and how do we apply them, then the question is how you do quantum programming. So to do this, you actually use quantum programming language, so nothing crazy here. Then to name a few, Qiskit is probably the most popular. Cirq is the one developed by Google. Qiskit is developed by IBM. Q# is, you guessed it, developed by Microsoft. And what it looks like to program on a quantum computer. So actually, it's Qiskit and Cirq are just Python library. and I will explain you this. So, do you? No, you don't see my. Yeah. So here, this first line, this yeah, whatever. So the first line here, QC quantum circuit 22. I'm basically telling to the computer, to the quantum computer, to create. So it's not really like what I'm gonna do is like I'm gonna create a circuit, and this circuit is gonna be then upload to the quantum computer, and the quantum computer will execute the circuit. Okay. And here I'm creating the circuit. So the first line here is quantum circuit 22. I'm creating a quantum circuit with 2 qubits and 2 bits. Then I'm saying here, oh please, on the qubit 0, you will apply a Hadamard gate. On the qubit 0 here, you will then apply a control NOT gate with the other qubit, qubit 1, being the control qubit, and then you will measure all those qubits. And this is basically exactly what you can see here. The qubit 0 here is have an Hadamard gate, and then you have this control gate here that will be applied to 0, with 1 being the control NOT. And then you will measure those 2 qubits here. And that's how you do quantum programming, and that's how you do the stuff. The idea of like your algorithm is to find and to be able to manipulate, to find a good like set of like gates that will manipulate the quantum state the way you want to have like your stuff being executed in the way you designed it. Okay? So now it's the big time. It's the live demo. So may the demo gods be with us, right? So here what I'm going to do is I'm going to break RSA live. Yeah. So I'm going to break RSA live on a quantum computer. So I'm going to use the Shor algorithm to break RSA. And now it's the little catch. Actually, I'm not going to use RSA 2048 bits. It's only going to be RSA 4, which is 4 bits. So in other words, we're going to find prime numbers of 15 using a quantum computers, but it's going to be a real quantum computer in the cloud. And this is thanks to... And nothing, wait. Okay, perfect. So, to do so, what I need... So I'm going to show you. So here, actually, IBM give you the possibility to run a quantum algorithm on quantum computers in the cloud. It's free. I think you have 10 minutes per month, and you absolutely don't see what I see. This is. So here I'm on IBM Cloud, and here you can see those are instances. Those are like 3 quantum computers that I have access to. And this is my instance of IBM Quantum Platform. And I can check oh, actually, what are the instances? So this is my instance that has access to this quantum resources. This quantum resources, each of them is a quantum computer. You can see you have some characteristic. This one is called IBM Toronto, has 131 qubits. This one is called IBM Brisbane, has 127 qubits. If I click on them, I can have a lot of information regarding this. So for example, I can see here, these are all the qubits and how they are connected. This will play a big role the way you will do algorithm on them. So this is how it's working, and you can check for each of them their properties. So that's the playground. So now let's play, right? So let me find, yes, this. So here is my VS Code data. You don't see much, right? Better. And I actually don't know how. Okay, cool. Thank you. So this is my code. Here, I'm doing a lot of checks. I'm doing a lot of carefulness to be sure that it's gonna work. But basically, I'm gonna execute a Shor algorithm. I'm not getting too much into details on how a Shor algorithm is working because it's a lot of math and a lot of tricks, and it's actually not that easy. But basically, let me find a moment where I'm configuring the thing. for you. Excuse me. Okay, whatever. Yeah. So here I'm basically connecting to the backend, which is like my instance on IBM, and then I'm gonna create the circuit, which I don't find. Yeah. And the circuit is whatever. Not that interested. Yeah, boy, no problem. So no matter what, we're gonna execute the code, and you're gonna see. So this. So here I'm connecting to the IBM Quantum Access, right? So if this is working, then we should be Gucci. And yes, okay. So that's good. So that's just me being like able to log in. So after I can choose between the three like quantum computers. So you see I have Brisbane, Sherbrooke, Torino. You have the different like the different characteristic of those computers. You can see that they have like a lot of qubits, certain have like different type of gates, and you have also all the jobs that are like in the queue. This number is not so like not representing what's really in the queue, but whatever. I'm gonna choose Torino. So if I'm choosing Torino, it says, okay, so Torino is like valid, it's operational, you can try to use it. This is like more like a breakdown of like what you're gonna do. Do you want to continue this demo? Yes. And now, if I do one, which is, are you sure you want to execute this code like on a real quantum computer? Then if I'm putting enter, we should be good to go. What I'm gonna show you is, I have those workloads here. So this is all the code that I'm running. So when I'm creating here, if I press enter, we'll have another workload that will appear here, and that will be basically run by the quantum computer. So what I'm doing here is like, okay, I have the circuit. I'm gonna upload the circuit to a quantum computer, and the quantum computer will have this in his job queue, execute this, and will give me the result, right? So over like the Wi-Fi, the Qi Wi-Fi of an auto, we're gonna be able to run show algorithm on this. So you see it sent the job. I think if I refresh this, and yeah, it worked. So you see I have one more job, and now like this was able so to run the like show algorithm, and we're able to find that like actually we broke RSA 4 again, so nothing crazy here, but pretty cool already. Which is 3 times 5 equals 15. So basically, this is you running code on the quantum computer live. Ta-da! And the only reason why we're not breaking RSA 2048 is because it's IBM fault. They don't have like a good enough quantum computers, but we have the algorithm working, and it's only their fault. But actually, it's a good thing for us, I think. So yeah, so that's how you do it, and I guess the demo guys were with us, so we're happy. Yeah, thank you. And now, the other algorithm, which is the Grover algorithm. I told you this one is less scary because it's only a square root speed up. So this one is really gonna change brute forcing and how you brute force basically symmetric algorithm. So the way, to give you an example, we can take AES 256. With a classical computer, you have to do to the power to 256 operation. On a quantum computer, it will be the power to 128 operation. And this is the square root speedup that I told you about. What it implies? It implies that like basically all the symmetric algorithm will have their complexity halves by 2. So halves, sorry. So you can see here like some algorithm, And the problem is like, for example, if you have something around 128 bits, it will go to 64 with the Groover algorithm. And this is like considered not secure, right? So how can you face this? Actually, you have to increase the key length. The problem with this is like it comes with performance issues. So the longer the key, the longer it takes to process. Storage, larger key means like larger key storage requirements. And also we have usually we take for granted the like encryption protocols we're using in our different software and different stack. So usually we don't have any way to change those like protocols, and they are hard coded in many ways. So this is a big issue if you want to move from this. So now that we've seen quantum like algorithm and we understood like how they were working on the physical side of things, we're gonna see like the real toys, which are like the quantum computers and what's behind and all the quantum news that you've heard about. First of all, quantum supremacy using a programmable supercomputer. So this is like the title you will see. This is the photo you will see. You're like, oh my god, that seems so cool. Like, are we done? Quantum supremacy? Like, what is it? Like, I want to be part of it, right? Actually, there is always a but. So quantum supremacy was a term invented to say that it will be the first time where a quantum computer will process data faster than a classical computer for the same information. So if you want to get the same results using a classical computer versus a quantum computer, if the first time you will have the quantum computer being faster, this is what we call quantum supremacy. Google achieved this in 2019, and like the announcement was this announcement was huge. But the reality of this is like actually they solve like an artificial sampling problem, which is basically useless. So it's like they took the best algorithm that you could run on a quantum computer, and it's basically also one of the worst algorithms that you can run on a classical computer. And they were like, oh, look at this. We were way faster than a classical computer. And they were like, yeah, sure. So it's like running against like someone 100 meter with like no leg. And you're like, oh yeah, sure. They will take more time, but it's designed like for people with legs. So they were like, yeah, sure. So that's the idea. So it's useless. So the crypto impact for us is also is none. And the actual there is actually it's already like an improvement and an achievement. So I'm not gonna say like it's bad and they've done a bad work. Actually, it's an amazing work that they were able to achieve. It's just like the impact of this result is not what you could think of when you heard about like, oh, quantum supremacy is here and we're done. So now we have a new term that is called quantum advantage. Quantum advantage is like if you prefer quantum supremacy 2.0. Basically, it means that like it will be the first time you will solve a quantum a problem with a quantum computer, but a useful problem, and this will be a real like game changer. Also, we didn't start to. I didn't like talk about like the number of qubits in quantum computers, but you're gonna see here there's like a big misinformation, to say the least, around like the way the press is like talking about quantum computers. Usually you say, oh, actually you have 1,000 qubits. Oh, actually you have 2,000 qubits. Oh, and like who has the higher number of qubits wins. And it's not like that. It's actually you have a quality of qubits associated with this. So in this case, IBM released the first ever 1,000 qubits quantum computers, but those qubits are what we call very noisy and short-lived. And they are like so basically bad, not bad, but like they are like difficult to drive in a current manner, such that it's not useful and you cannot run any meaningful algorithms such as like Shor algorithm or order algorithm on them. But at the same time, being able to achieve this kind of step is pretty amazing. It's just like only advertising your results in the press on the number of qubits can be misleading, because you could say, oh, actually all the qubits are the same, and actually qubits are not born equal. And the reason behind this is why qubits are different. It's because we have a problem which is called quantum decurrence. And I told you, like, when you have basically to do like all those work on those like qubits, right? Those qubits are super sensitive states, and those states are like really sensitive to noise. And if for any reason they like receive electromagnetic noise, they can switch and they can basically leave. You can see here in this animation, you were like doing your operation, you were like smoothly changing their states one like step by step, and if they're like they're gonna absorb some noise, they will like basically flip, and they have like different ways to flip. And doing this, they will basically you will lose track of the trajectory of the spin of the qubit, sorry, and this will basically ruin your like calculation on your quantum computer. And actually, one of the big limitation is how long can you track, how long can like you can operate a qubit without it being like how long can you run like and drive a qubit without the qubit being flipped, so being like untrackable. And this what's limit your time when you're doing like a quantum algorithm. Actually, what happened is like, oh, I have like few milliseconds to execute my code, because actually after this time, I consider like one of my qubits will basically have this decoherence moment, and I will not be able to be certain of like, oh, what will be the outcome of my algorithm, and I will not be able to guarantee that like my algorithm will give me a good result. It will be like kind of like a bit flip on a classical computer. And now it's the fun part. If you add multiple qubits, I told you before that those qubits will be entangled. Being entangled means that like they have their like characteristic are linked together. So if you have an assemble of qubits like this, let's say 8, or it could be 1,000 or 4,000 or 10 millions, if one of them flips, basically the whole state, so the whole quantum computer is gone, and you cannot use it. It's not like, oh, actually only one of them flipped, let's use the other. It's not like this. It's not like this in quantum computing. So you try to do a lot of stuff to avoid this, and you try to do what we call to implement error codes. So with this in mind, there is, even if it sounds really difficult, there is no like theoretical roadblocks for us to have a powerful enough quantum computers to have like a meaningful, an impactful breakthrough in cryptography in the coming years. The only thing that we see is engineering challenges. So at the moment, we don't have like, it's not like, oh, actually we know that like physics up to a point will have this issue. It's like, oh, actually there is no issue. You just have like to work harder to find like a good way to protect your qubits and do those codes and like extend those like quality of those qubits and the number of qubits. But you should be able to do it. And if you're able to do it, you'll have like a powerful enough quantum computer. So now let's see the quantum computers, the real guys. You have many types of quantum computers. You can think of this as like the beginning of classical computing, where you had different kind of like technologies that will like battling to find like which technology we're gonna choose to apply. Sorry, I have the words in French. So we choose the technology which is the semiconductors, and the semiconductors are the one we're using to do logic gates. So the way you do logic gates is like with semiconductors, and you do FET, you do all those fun stuff. At the moment, we're still there are still like a competition between different type of technologies, because different type of technologies have different trade-off. So in classical computing was like semiconductor versus like lamp or all those fun stuff. And this is, we're at this stage at the moment. So what I mean by this is like you have what we call superconducting qubits here. They are living in these kind of like giant cryostats. And those cryostats are like a big fridge. And you will operate those qubits by sending microwave along the lines that you are seeing on the picture. And you will address those qubits like this. You have what we call trap ions. Trap ions are basically individual atoms trapped in like electromagnetic fields, and you will address them with light lasers. So you have like lasers, so you have like those ions in those kind of chamber, and then you have like a whole like optical setup behind this to have lasers that will point at those like specific atoms to send like specific like operations to them. And this is how you will apply the gates I showed you before. Then you have topological qubits. Those are like another type of superconducting qubits. You've heard of them recently because Microsoft made a huge announcement of like being able to produce some. It's actually open to a lot of like controversy, so we'll see. Those are like really nice, like superconducting qubits, because by nature they should be really protected against this like errors that I was like talking about before. So yeah, and think of this as like actually you have like a lot of different like technologies. So we don't know which one is the best at the moment. Every technology has trade-off. Some will be better on like, oh, actually we have less errors, but the way you will apply the gates and will take more time. But so this time is something it's a scarce resources. So you want also technology that will allow you to apply gates in like at the smallest time possible. And so we are still like, there's still a big battle. And this is also why you're able to see startups that are like doing quantum computers, is because those startups backed by like millions of dollars. So we're not talking like two guys in a garage, right? But the idea is like they have a specific technology they are believing in, and they're like, oh, actually, sure, we have some trade-off, but we think that we can overcome those trade-offs with clever architecture on our side. So this is why we're able to fight Google on their like quantum race, or fight IBM on their quantum race, right? So now that we have seen what are quantum computers, what are quantum algorithms, that we have run a quantum algorithm on the quantum computers in the cloud, we're going to understand what's the threat timeline, the risk, and all the post-quantum solutions, so all the post-quantum cryptography that is already in place and that is being developed at the moment. So just to understand, the best quantum computers we have, so I told you about IBM with a quantum computer with 1,000 physical noisy qubits, and I told you that like, and you know that like all the qubits are not the same. So the way we're thinking of this is like actually you have higher quality qubits, but you can also say you have logical qubits and you have physical qubits. So logical qubit will be a perfect qubit that will have like no error and that will be able to correct itself. And to have one logical qubit, you will have like basically multiple physical qubit that will give you this logical qubit, right? So if you need for a computer, let's say for an algorithm, you need 4,000 logical qubits. Actually, the number of like qubits you need to produce will be this times like 100 or times like 1,000, depending on like the architecture you're gonna choose to avoid those errors, right? So with the quantum computers we have at the moment, we're far from being able to break anything regarding RSA 2048. We can only factor small numbers, 15 and 21, and find those prime factors. We can do simple optimization problem, and we can do simulation of quantum systems. So to break RSA, we need 4,000 error-corrected logical qubits. So this is the number of qubits I mentioned. So those 4,000 logical qubits will give us the possibility to break one RSA key per day, if we're able to operate them and to run the show algorithm on them. At the moment, there is not like one experiment where we have like one logical qubit that is working 100% of the time. There is no way for us to have like an infinite time lifetime for a qubit to work on. So we are far away from this, and we're doing physical qubits. All the numbers that I was giving you before, the IBM numbers, like the 1,000 qubits, those are physical qubits. Those are not logical qubits. So you can see that like with the best estimation, best case scenario, to do to break RSA, we need 100K, so 100,000 physical qubits. At the moment, the base guys are doing 1,000 qubits, and they are not really good qubits too, physical qubits. So if you ask people like how long it will come before, like how long it will take before we're able to break RSA, depends on who you ask, right? So if you ask the guy like making quantum computers, they will say, "Oh yeah, by 2030 we're done, guys. Like it's like we'll be able to collect the money. So please VCs give us more money, right? Only 5 years to hold." If you ask the more skeptical guys, and usually the research community, they will say, "Oh, it might never happen. Like we never know. Like engineering, like the engineering challenges we have to overcome are actually crazy." And it will probably take us more than 3 years, and perhaps we'll never be able to overcome those like engineering challenges. And the academic consensus is like balance, and they're saying like crypto breaking kind of like quantum computers will be there in 10 or 20 years. Nobody knows, obviously, so it's like Sometimes you wish they are like here sooner so that you can do a lot of things, but also it's gonna shake a lot of stuff if they're like arrive tomorrow. And the reason for this, like one of the big thing to take care, like, and one of the big threat and the big risks is what we call like this attack, harvest now, decoup later. And this is a current attack that is happening right now. You guys are being attacked. And this attack is in two phases. You have the collect phases. This collect phases is basically the fact that we're collecting emails, VPN traffic, databases, backup, whatever you want that you can see. Doing so, you're using network taps, so you're tapping the data, you're like collecting data breaches, whatever that is encrypted. You don't mind, right? So you collect everything that you can. And then you have like a massive pool of encrypted data with the best algorithm we're using at the time, RSA 2048, and all this fun stuff. And then phase 2 happen. You have a quantum computer that is working, and now you can decrypt. And so what you will do is like you will take all this data, and you will put this data in a show algorithm, and you will get all this decryption for you. And in this case, what will happen is like, oh, actually all the previously collected RSA encrypted data will now be like crystal clear for you. And this is pretty fun because like you can start to collect now. Actually, all the good guys like are already collecting your encrypted data. And if you think about it, like if you are able to track that, oh, actually these packets are super important but are encrypted, it's pretty like the value of just storing this data is actually pretty cheap, and just wait to see if you have like a quantum computer that will emerge in like the coming years. And this is the retroactive decryption of 10 plus years of like secure communication is definitely something that will have an impact. So this is where you have like a lot of fun, a good like Friday. But like if you look at this, you're like, oh my god, this is the end, like we're all done, right? Actually, we have some good guys. So the 3layer+1 agency that is looking out for you, the NIST. And NIST was able to, is actually working on implementing what we call post-quantum cryptography. Basically, it's like, you could say it's quantum proof or quantum safe cryptography. What it means is like, actually, if you are using encryption algorithm that is not leveraging this prime factor that I told you about before, which is what show algorithm is good at, then you're actually quantum safe. And there are like a lot of like way to encrypt data that do not rely on this, that you can use, and that will make your data and your way you communicate quantum safe. And the idea is like those guys like created like a competition. They had like 82 algorithms that were tested and that were like candidates to find like which will be the winner and which will be the de facto algorithm. At the end, they found like 4 algorithms. They have one algorithm, like two. They have like one algorithm, 2 type of algorithm. We have what we call key exchange mechanism algorithm, and you have digital signature mechanism. So one is for RSA, and one is for AES, basically. If you do this, then basically you have like a collection of algorithms that you can use that are quantum proof, and are like you can run them on like a classical computer. The idea is that like you will not encrypt your data using basically the thing that quantum computers are good at, which is finding prime factors on big numbers. So those winners, those algorithms, like the main one is called MLKEM. Whatever. You can find like if you have problem to sleep, you can definitely go on the NIST website and look at those like definitions and like all this PDF documentation around those stuff. It's definitely interesting, but not for the faint heart. And then when you have this, basically it will be when at the moment they find the winners, and they are like, I think they are discussing about like how you will have a standard, right? How you will have like standardization of those algorithms, and what will be the next way to do encryption between classical computers. And when we have the standard, then it's gonna be our turn to apply the standard. So you will change like the de facto like algorithm you will use from RSA to actually those ML-KEM. sounds like a lot, but we already have like historical precedencies around like changing algorithms. So from DES to AES, from MD5 to SHA-256. So we've done this before. The idea, and usually something we consider for granted, is that people are basically usually hard-coding the encryption in the program, and what you want, actually, it's kind of like a layer when you can like choose what type of algorithm you want to use for your tech stack. And this is the way for you to be like agile in your cryptography to avoid all this fun stuff. And you already have people that are using this. So you have like the big names, Google, Cloudflare, Signal. Signal is actually doing something pretty nice. Signal is using like a combination of a classical and quantum safe algorithm. So it means that like both of those two algorithms have to be broken to be able to like decrypt the data. So they are using this kind of a combination of like both words. And more and more like tools are using those like quantum proof algorithm, and you can actually use them. And also there's another live demo, but actually it's actually super anticlimactic, so I decided to remove it, which is basically you can set up your SSH server, OpenSSH server, to use a quantum safe algorithm already. If you have the latest like OpenSSH 10, and if you have this command, you can choose the key. You can choose the algorithm, and you can actually, this algorithm is like a quantum safe algorithm. So this is like how you can do SSH with a post-quantum cryptography. And so yeah, this is like, I guess in my book, a lot of cool points on internet. Yeah, and now the conclusion. So we are able to bust a lot of myth, right? So quantum computers will break all encryption instantly. Actually, no, it's not working like this. We have certain type of encryption that are using certain type of like mathematical trick that will be broken by quantum computers. We need to panic and replace everything tomorrow. We have some time. We have this like harvest now, decrypt later problem, but for the rest of like, for majority of your data, it's not a big issue. Current quantum computer can break RSA? Absolutely not. You've seen this. You can break RSA with 4 bits, but not more than this. Quantum computers will replace classical computers. It's actually not the case too. I showed you 2 algorithms. One of them was really, really fast, and the other was like, okay fast, right? So you have to understand that like you have to have some specific quantum algorithm that will be way faster than classical algorithm, and not everything that you're running on a classical computer can be accelerated the same way I show you with the show algorithm. It's only a small subset of algorithm that we know for sure are accelerated like this in other ways. Post-quantum cryptography is unbreakable. Actually, we don't know. Oh, I missed one. Google IBM quantum supremacy means crypto is dead. No, I told you that like quantum supremacy is only like you run a calculation faster than a classical computer, but this calculation can be meaningless, and you'll be good to go. Post-quantum crypto is unbreakable. It's not the case because like you never know. And this is why actually NIST took multiple like winners in case like one of their like chosen candidates is broken in any ways, then they have like fallback solutions. Secret governments quantum computers already exist. This is also false, and this is something like usually people ask me about. So the community doing this and working on quantum computers is pretty small. It's small enough that like everybody knows each other, and if someone was close to have a like working quantum computer, probably that like some guys from like some countries will knock on their door and say, hey, please work for us, and don't tell anyone what you're doing. So actually you will watch the silence, and if someone goes silent for a long time, you will be able to tell because the community is small enough, like, oh yeah, have you seen James? No. Oh yeah, me neither, for the past 2 years. Where is he? Oh, I don't know. And then you can start to wonder. At the moment, everything is public. Think of this as like LLM before OpenAI. all the research was public. Everybody was sharing the information. No one was like hiding anything because you are so far away from the goal that like you have better chance to achieve this goal by sharing the information. And now I've told you about like how bad quantum computers are and like what it will create for us, like all those like bad Fridays and bad weekends, and when we'll have like powerful quantum computers. But actually, quantum computers, and I want to leave you on this happy note, will help us to do a lot of fun stuff and really nice stuff. So basically, we'll be very good at like simulating like molecules, and simulating molecules give you the possibility to do drug discovery, give you a lot of possibility to do material science, and a lot of like climate and energy science, which is something dying at the moment. So with quantum computers, it's not only bad. You also have like other algorithms that are not related to crypto that will be accelerated, and those algorithms could have like meaningful impact on those like topics and on your life. Voila. Are you all dead? I don't know. Thank you very much. This is you can find me on like Discord, LinkedIn, and my personal blog. Do you have questions? Yes, sir. Oh, sorry. Yeah, so you have times associated with them. So depending on the qubits, I'm not sure if you're talking about this, but like if you're talking about like decoherence, you have usually times, and those times are characteristic depending on the technology of the qubits. And you have like like if we go in a bit more details, you have usually two type of like errors that you're associating with times, bit flip and phase flip, if you want to look for those terms. And depending on the technology, you could be your like lifetime of your qubit could be milliseconds, seconds, and that's it. Seconds being like the longest. Usually the superconducting computers I showed you, which are the platform with the most advanced result at the moment, have lifetimes around milliseconds. So you can only do a calculation like during this small period, and then you have to like basically reset the whole quantum computer to do another calculation. Yes, sir. So basically it's always the same thing. You apply this like exponential like acceleration, and the thing is like at the moment you have if you're able to have like RSA 2048, you will be able to also accelerate the same way like RSA 40 and 96. So you will have the same like problem, and you will also like if we're able to reach this goal and we have like this powerful type of quantum computers, then we will not be far away from being able to have like even more powerful quantum computers. It will mean that like basically we will overcome like all the engineering challenges. Say that again? I don't know this one. Oh. This one? Yeah, okay, yeah. So I don't that's a quantum proof one. So so I don't know all the algorithm, but basically the idea that you want to think about is like, is it quantum proof? Yes, no. Is like, do you use at any point this like prime factor, finding the prime factors of a big number? If yes, then you're not safe against quantum computers. If no, then you're good. Like one of the technology behind this is the winners of like the NIST are using lattice-based encryption. I don't know if this rings a bell, whatever. So it's another way to encrypt the data. And voila. Thank you very much.